heavy workload. It's an honor to have him here. And of course, we would like to thank Mr. Sterioula because they will have a very important discussion together. So I'll not take much of your time. The discussion will be in English. Well, in Greek from Mr. Sterioulas and in English from Professor Retsolas. So for those who do not understand English, they can get headsets from the reception. Okay, let's start. First of all, I'd like to thank the Editions Sophia for this invitation. Ladies and gentlemen, dear colleagues, dear students and lovers of physics and the universe, it's a great honor to present you a very important book that was written by a distinguished scientist in astrophysics. So the irresistible attraction of gravity is a journey for the discovery of the black holes, which was written by Luciano Rezzola. As a professor, as a colleague, as a professor of astrophysics, I followed So before we move on to... Can you hear me now? Can you hear me now? Okay. So before we move on to the content of the book, I would like to mention some important elements of his curriculum vitae. So he's a professor in Frankfurt Astrophysics University, and he's interested in the gravitational waves with theoretical and calculation and methods. He has written over 300 research publications and articles and a book on hydrodynamics. He is a member of the board of directors of the Event Horizon Telescope, which gave us the first image of a black hole. That was an achievement that was considered to be the image of the century. And he was awarded the different awards and, of course, the golden stamp of the University of Bari. And for his contribution in this experience, he shared one of the most important awards, the breakthrough in fundamental physics, and the Einstein Award, together with the other members of the team. These awards, of course, reflect the impact of his work on the scientific community and on the, of course, the secularization of the book. So. This specific book, The Irresistible Attraction of Gravity, that was translated by Vastilios Tergezis and is published by the Sophia Editions. So Luciano Rezzola guides us in a very significant journey based on the gravity theory. So the book is structured in a way that guides the audience, starting from the main principles of gravity, as described by the top scientists of the previous centuries, Galileo, Newton, and Einstein, until the research that is conducted and enlarges our knowledge today. One of the most fascinating chapters examines how the presence of the mass curves the space and time, which is a fundamental element of the gravitational theory of Einstein. This property explains many of the phenomena that we discover in the universe, such as the black holes, the gravitational waves, and the neutron stars. And it also plays a very important role in our daily life through the calculations that are made on the GPS system, which we all have in our mobile phone and that we use in our cars. So in another chapter, the author describes the main characteristics of some stars, where all the theories of physics, such as electrodynamics, and even the theory of a solid status must cooperate in a harmonic way in order to explain the properties of these stars. However, these stars cannot have an unlimited density, so where the possibility of their existence starts the black holes, which are examined in another chapter, in a subsequent chapter of the book. So we use the entire physics in order to describe this physics. And as regards the black holes, we use the relativity theory in order to explain them, and of course the observations that are made. And they are described by two quantities, the total energy mass. And from this point of view, the black holes are among the most simple objects in the universe. The book also describes a description of how the Horizon Telescope observed the first image of the black hole in one galaxy. This historical achievement required the cooperation of the most capable radio telescopes that are found widespread all across the planet. And in order to produce the black hole in our galaxy, new technologies and new data processing methods were used. The last chapter of the book is dedicated in the other effect of the other on the gravitational waves. Since 10 years, when we started observing the gravitational waves using the LEGO detectors, and in Italy, close to Pisa, we found a new way to control of the gravitational waves. Luciano Rezzolla describes how these are created, how the fusion of the black holes occurs, and of course there is a wealth of knowledge that we obtained from observing the first fusion of two neutron stars that was observed with gravitational waves and electromagnetic waves. That happened back in 2017. The critics have, of course, to praise the capacity of Mr. Rezzolla to explain all these gravitational physics phenomena. Geraint Lewis, one distinguished astrophysician, describes it as an important internal history in one of the most important scientific endeavors in an era. So also we see what happens in the efforts that were made in order to get the first picture of a black hole, which of course witnesses the cooperation and the capability that are required in order to achieve that. What makes this book unique is the passion of Rezzolla to make the very complex ideas, to make them sound simple. To conclude, the book entitled The Irresistible Attraction of Gravity is not just a book, but it's a call to explore the deep beauty of the universe through the eyes of one of the most dedicated researchers. Then, I would like to raise some questions to Mr. Rezzolla. And after he answers, you can also raise some questions. He's here for that. He's here to answer to any questions that you may have on the universe. So, dear Luciano, thank you very much for being here in Thessaloniki. I would like to ask you a couple of things. And first of all, I will start by asking you what inspired you to write this book. Was there a specific moment or experience that pushed you to share your knowledge in this way through this book?
Thank you, Nick, for the nice introduction and summary of the book. Thank you all for being here. and apologies for not speaking Greek. This is one of the things I would like to learn in the future. I have a very strong bond with Greece. I spend a lot of time in Greece and I love the country. So, you know, as just like you, as a scientist, I have a full agenda. And just like all of our colleagues, I tend to think that, oh, my job is to do research and to write research papers. And I possibly don't have the time to explain science to people who are not experts. So for many years, I've seen my only role as that of talking to my peers, the same people that work with me. Then something happened that changed this view, and that was COVID. All of a sudden, I found myself having more time than in the past because I was not traveling, I was not spending so much time in the office. And I thought, okay, I should try and do something that I always said I should do and never did, and it is try to write a book about science. And my goal was I should try and write a book that my mother can understand. My mother is not a physicist, my mother was a school teacher, elementary school teacher, and she always wanted to understand what is it that I was doing. And I tried many times talking to her to explain this, but it was always short conversations, and it wasn't really a systematic approach to the problem. So I was trying to explain to them that I was working on black holes, on gravitational waves. She was always very interested, but she could not really understand. At one point she would say, but there is something you haven't told me. And I thought, okay, I should try and start from scratch and explain what is gravity. And that's how the book came. So the book came from COVID and from the desire to explain to my mother what is it that I am actually doing. Now, that's the genesis of the book. But the lesson I have learned is that we as scientists are doing the most interesting job possible, and we are even paid for doing this. And we have to return something to the society that pays for us, right? You all are paying our paychecks, and I thought it's important for you to know exactly what are we doing, and not just our colleagues. And so this is my attempt to convince my colleagues that a scientist can be a scientist, do state-of-the-art research, and yet talk to people, to the public, because that's part of our job. At least in the 21st century, scientists have to return something back to the society. And that's why I think I hope to give an example with this book.
All right. So, η καριέρα σας περιλαμβάνει πολλά...
Oh, your career contains a lot of achievements in astrophysics. What drives your passion for phenomena such as black holes and neutron stars?
Okay, so gravity here on Earth, in this room, for instance, is very weak. And so from a gravitational point of view, it's actually boring. Things are very simple. Nothing special happens. Light moves on straight lines. There is no time dilation. There is no relativistic effect. But there are places in the universe that we've learned exist where gravity does very different things from what we see here. So my curiosity comes from exploring gravity in conditions that are very, very different from the ones we are used to. And under this condition, the craziest things happen. It's a bit like what is it that motivates a biologist to study the strangest animal? Because, you know, by looking at the strangest animals or the strangest phenomenon or the strangest set of chemical reactions, we actually know much more about the simplest reactions and animals. So it's a curiosity coming from wanting to look at the extreme manifestations of curvature and gravity. And these are given by black holes and neutron stars, which are, if you read the book and you learn about them, you just think, no, come on, this is not possible. I can't believe that really there are things like this in nature. They are completely different from our experience. And they also pose very difficult questions about, what is it that we understand about nature? So that's really the motivation, trying to understand what is so different from us.
Όταν επικοινωνείτε με το κοινό, ποιες στρατηγικές χρησιμοποιείτε?
When you communicate with the public, what are the techniques to make these difficult scientific concepts as far as easier as possible for the general public?
The target was my mother. The experience in explaining these things come from my children. As they are old now, they are 20 plus years old. But since they were young, I try to explain to them science in very simple terms. And then they taught me that, my language is not adequate, that I have to start from the language, and that the best way of explaining something is using the proper language, and more importantly, analogies. That's what the book is all about. It's trying to explain gravity, even the most bizarre concept and most difficult concepts, in terms of analogy. And if you see within the book, you will find episodes where I say, imagine that, or imagine that there is this situation, two people going on a spaceship near a black hole, or two people falling onto a neutron star, and things like this. I find that through analogies, we can actually break the walls that prevent people from understanding otherwise very complex concepts. I have coined a word. I don't know how easy will be the Greek translation. In English, this is called cognitive empathy. So it's the empathy, something that we all understand, the ability to enter into the other person's, mind or feeling, but it's a cognitive empathy. It's the ability to enter into the level of knowledge that the other person has. And if you try to do this, and if you have children, you have learned how to be empathic in terms of knowledge with your children, then everything comes much more easy, because you realize that, okay, the person that I am trying to talk to is not an expert like myself. And I have to ask myself, what is it that this person knows? What are the languages or the words or the experiences that this person has? And how can I use these experiences to explain a concept? Just to give you an example, in the book I try to explain how time passes differently when you are near a black hole. And there is this episode of two characters. Actually, one is my wife, and the other one is my son, who are near a black hole, and they are on a spaceship, and they want to go and visit closer to the black hole. So they take off on a smaller spaceship, and they get closer to the black hole. Before they do this, they leave on the table some cookies that they had prepared for having tea. They forget them on the table. Then they go to the black hole, they go around the black hole, and they come back. For them, nothing has happened more than in a couple of hours. But when they return to the larger spaceship, which is further away, they realize that the cookies have all gone bad. They've all been attacked by mold, and they are no longer eatable. And that's an example how you can imagine, with a language and experience everybody knows, how time passes differently in different positions in space-time.
Πολύ ωραία. Τώρα, στο τέταρτο κεφάλαιο του βιβλίου σας, αναφέρεστε στο γεγονός ότι
Now, in the second chapter of your book, you mention that when the general relativity theory was proposed, but also the general relativity theory, initially there were many reactions even within the scientific community. Later, this changed when we had observational confirmation and experimental confirmation. Can you imagine something similar today? Is there a theory today that is faced with a reaction, a strong reaction by the scientific community, but can be confirmed by experiments and observations?
To be arrogant when it comes to knowledge. They think they are the possessors of knowledge and that they know how things work. And this is well justified because scientists are experts of a given field, and as experts of a given field, they think they know how the laws of physics behave. And sometimes this means that they tend to be conservative. They tend to think, I know how the large majority of the community thinks, and I believe that this is the way things should be work. And this has happened ever and ever and ever in the history of science. You know, at one point, Aristotle, you all know about him, well, he was coming up with some explanation about gravity, about planetary motion, and so on. And for many centuries, no one debated this, right? Because Aristotle had said it, and it must be right. And sometimes we tend to have the same attitude. We think that because everybody believes in a certain way of thinking, that must be right. And when Einstein proposed his theory, well, it wasn't really well received. They thought, okay, gosh, this guy is predicting something that doesn't make any sense, and we don't really understand. So who cares about this theory? The only reason why they took him seriously is because Einstein was very well known for being a very smart person. He had already received a Nobel Prize for a different reason. And so they must have thought something like, okay, this guy is smart, this is an interesting idea, but it's irrelevant. Let's just forget about it. And it was later, in the 50s, in the 60s, when new observations revealed that things existed that could not be explained by the present knowledge, or knowledge at that time, that they went back to Einstein's theory and realized, okay, maybe this object, the black hole that this guy has predicted, maybe this is it. Maybe this can explain the observation. So I think we often have this attitude, and we have always to remind ourselves that what is considered to be exotic in our time may become perfectly acceptable in the future. And it's only by having an open mind that we can be the real good judges of what is realistic or what is possible, and dismiss what is really just wrong because it violates the laws of nature. Sometimes we tend to say, okay, because this is not mainstream, cannot be right. And we do this very often. Just, you know, the idea of black holes were produced as a solution that were not discovered by Einstein. Einstein found the equations, and 6 months after he found the equation, there was someone from Frankfurt in Germany, Karl Schwarzschild, who came up with the first solution. And this is the Schwarzschild solution, which is a solution of a non-rotating black hole. Neither Schwarzschild nor Einstein understood the solution. They thought, okay, this is a very bizarre, certainly it's correct, mathematically correct. And that solution for many years was ignored. But nowadays, everybody is very familiar with the idea of black holes because we think them, okay, it's part of our culture. So maybe there are new ideas that are now considered exotic, impossible, unlikely, But as long as they satisfy the equations and they are mathematically correct, I think they deserve to be considered as possibilities and therefore reserve a portion in our understanding and in our knowledge.
Okay. Στον επίλογο του βιβλίου
In the final
έχει η ευκινησία του ανθρώπινου μυαλού και η φαντασία που έχει ο άνθρωπος, τη δυνατότητά μας να επεκτείνουμε συνεχώς τα όρια της γνώσης. Πιστεύετε ότι στο μέλλον,
Do you think that in the future, when AI will most likely dominate science, allowing an automation conductance of the research, to have a saturation due to lack of imagination? I'm sorry. Oh, okay. Oh no, okay. Yes. Yes, I will translate it. Can you please ask him to say it in English, please? In Greek. Thank you. So in the final part of the book, you stress the importance of the flexibility of the human mind and the imagination of the human mind when it comes to expanding the limits of knowledge. So, do you believe that in the future, when the artificial intelligence will most likely dominate on science, leading to an automated way of conducting research, do you think that this will result in a saturation due to lack of imagination?
It's a very deep question, Nick. I don't know if I have the answer to this. I think all of our knowledge comes from imagination. Before we find an idea or a theory, a mathematical construction that explains something, is because we think about it, we imagine it. And I think Greece is a perfect example of how much knowledge was produced before mathematics were even introduced or before physics were even introduced. Many of the natural philosophers in Greece had got right a lot of the details that make our present understanding of physics. The atomic idea, the conservation of energy, the transformation of energy. These are concepts that nowadays we express in terms of mathematical laws, even theorems. But these guys were able to come up with these conclusions by just thinking about it, by just imagining them and reflecting about them. So in my understanding of life and science, a lot of this science comes from thinking, pure imagination, beyond our limits and our experience. Now, this is something that characterizes us as humans, because we can imagine. I don't know if an AI-built machine can do the same. If AI can imagine and abstract and go beyond the basic knowledge that it has, then of course AI can produce science. But if not, AI will just use what we know and maybe not produce new science because it has this incapability of imagination.
Very good.
Which are the main questions, the main mysteries in astrophysics which fascinated you most and that you will work on in the coming decades?
One of the fascinations and big questions that I would like to work on is, there are two. One is, do black holes really exist? So you may think that I should not be asking this question, given that I've taken a photo of a black hole. So black holes are fascinating objects. We have made a photo that looks like a black hole, but black holes come with a lot of problems. The first problem is that they have an event horizon. That is a surface where information is lost. We know what happens inside a black hole because the laws of physics are known, but we cannot prove it. That's very frustrating for a physicist. A physicist wants to know and be able to demonstrate how things work everywhere in the universe. And all of a sudden, there is a region beyond which we cannot do an experiment. Well, we can do an experiment, but then we cannot tell anybody about the results. It's a bit like death, okay? We know that once we cross that line, we will know what's behind it, but it will be too late to tell anyone about what's behind. And the frustration is so large that I have this episode in the book where there are two characters outside a black hole, and these characters actually come from Galileo. Galileo also tried to explain science, creating analogies and characters. And the two characters in Galileo's books, the dialogue of the maximum systems, are Salviati, who is the wise person, and Simplicio, who is the simple-minded person. So they are on a spaceship, and they are going around a black hole, and Simplicio, the simple one, says, "Ha, Salviati, do you know what's inside a black hole?" And Salviati says, "Of course I know what's inside a black hole. I know this was revealed to us by the Schwarzschild solution, that is a solution of the Einstein's equations. No, don't bother. I know what's inside a black hole." And Salviati then answers, "All right, okay, so tell me, what's inside a black hole?" Well, inside a black hole, there is a huge ice cream shop. And they sell the taste, the flavor that I like the most. And Salviati is very upset. Said, no, it's impossible. You can't possibly have an ice cream shop because it would just be destroyed by gravity and it would be falling at the speed of light. Well, I don't believe you. And there is nothing you can do to prove me wrong. And Salviati is very upset because it's exactly true. All he can do is appeal to knowledge and equations, but he cannot prove that Simplicio is wrong because he cannot carry out an experiment shows him that he is wrong. So for a scientist, it is very frustrating. And there are now a lot of researches that are being made which are trying to come up with different solutions that are similar to black holes but are not black holes. The second problem that black holes have is that they have a singularity. At the center of a black hole, even Einstein's theory failed. We believe that this is due to the theory being not good enough at describing very small scales where quantum mechanics takes place. But right now the theory is incomplete. And because of this singularity, again, there are many theories that are trying to come up with objects that maybe are even black holes but do not have this problem. So I think it would be nice in the future to spend time thinking about this topic and see whether or not the idea of a black hole is something we have to cope with and accept, just like we accept death, or whether maybe there are other things that are there that are compatible with the observations we've seen, both in terms of gravitational waves and in terms of photos, but they are actually not black holes. There was a second thing that I would like to concentrate on, and is neutron stars. So neutron stars are also a big component of the book. Neutron stars are these wonders of nature. Imagine taking all of the matter that is in our solar system, so the sun, all of the planets and so on, and condense them into an object which is not much bigger than Thessaloniki. Thessaloniki may have a diameter of 20, 30 kilometers, but, well, imagine concentrating all of this mass in such a small object which is essentially spherical, that is extremely hot, extremely magnetized with a very strong magnetic field, that is, and has a rotation which is 700 Hertz. So this is 10 times faster than the fastest washing machine that you have at home. There is this object of 10 kilometers that is rotating and is no bigger than Thessaloniki. So these are fantastic objects. so far away from our experience. And I would like to understand what happens in particular when two of these objects crash into each other, producing gravitational waves.
Πολύ ωραία. Εγώ είναι αλήθεια, έχω και άλλες ερωτήσεις.
Thank you very much. Of course, I have some other questions, but I suggest that we accept some questions from the audience. It's a good opportunity, since we have Mr. Rizzola here, to ask him in order to get an answer. So if you have any questions, now is the time. Please use the microphone in order to be translated. Good afternoon. I'm not a physician. I'm a philologist. I was fascinated by the title of this book, The Irresistible Attraction of Gravity. When I read this title, I conceived it in not in a literal way, but in a metaphorical one. So I'd like to ask you if you selected the title in the literal way, so if this means what it says that it means, or if you had in mind the poetic, the metaphoric concept, and what is the content that you would give in case that you chose this metaphorically.
Thank you. Indeed, I have come up with a title. My publisher at the first version was in Italian, and they didn't like the title at all. They said it's too complicated. People like short titles. And I insisted. I think the title is exactly what I want to say. It tells you about gravity, and we all know that gravity attracts. But I want to stress that it's an attraction that is not just a physical attraction. It's irresistible, because it involves more than our knowledge. It's a part of our life. This is because gravity is the only physical force or interaction that we have an experience of. There are other forces, but we don't experience them directly. But we know about gravity. We know that, it took us an effort to come here, that there is something pushing us on these chairs, and we are not floating in space because there is gravity. So it's an attraction not only in terms of physics, but also in terms of our minds. And it's irresistible, because even, I don't know how many of you, but every time I go onto a very high cliff, I really would like to jump. I really would like to experience what it's like to be without gravity. That's what would happen. Of course, I don't do it, and none of you does it. But the fact that we want to do this is telling us that, we would like to experience even the absence of gravity. So I think I really like to go on a space station and see what's life like without gravity.
Ευχαριστώ.
Thank you. I'm a physicist, so I will ask two questions, actually, which are more specialistic. Can you tell us something about the materialization of the forces of nature? What is the peculiarity, what is particular about gravity, about the unification, the unification of the forces of nature? And the second question, we have experienced what is lack of gravity when we are in our mother's womb. We are within a liquid which has the same special weight as us. We swim in a space of non-gravity, but I don't know if we keep memory of that.
Thank you for the questions. I'm not sure I understood from the translation, but what's special about gravity as Einstein told us, is that gravity comes from geometry. It's, in fact, the equations that are behind gravity are the equations of geometry, of differential geometry, and tell us that space-time is not straight, is not flat, but actually is curved. And that the geometry, the Euclidean geometry that was studied here in Greece, actually is not the right geometry, and that there is a more complex geometry, and that gravity is just the manifestation, is the way we test the presence of this space-time curvature. The second question was?
This was about an embryo.
Oh, yes, yes. Yeah. So that's a very good question. There is a test, and I mentioned this in the book. It's called the Moro reflex. It's something that maybe you have experienced, or if you have seen your children being born, but this is a test that is done on very young children as soon as they are born. Few seconds after they are born, there is this test which is done to check the physiological, working of their this new nervous system. What you do is you take this child, this very baby, and you drop him. You don't really drop him. You let this baby experience an acceleration, a gravitational acceleration. And the reaction of the baby is to open the arms and try to grab something. If the baby responds in this way, you know that he is neurologically well functioning. And this is telling you that actually we do know about gravity. We have this instinct, or we have learned about gravity even before we are born. And this could be maybe an instinct we have developed when we were still some monkeys, and we needed to grab ourselves very young on our mother's backs, as monkeys do. So this is telling you that we have an unconscious knowledge about gravity, and that this is already there by the time we are born. Even if we don't know anything about physics, we know how to react to gravity. Thank you.
Ευχαριστώ. Καλησπέρα σας.
Thank you. Good afternoon. I would like to congratulate you on your scientific work and for this effort, this endeavor to try and bridge science with everyday life. That is to make difficult things look easier. Although I have studied, I'm from humanistic studies, I'm always attracted by science and the mysteries of science, because when we understand the macrocosm, we may find solutions in our microcosm, micro world. How many things we know about the universe? All I have read that we only know 5% of existing things in the universe about dark matter and dark energy. We know only 5% of the things that to be known about the mysteries of the universe.
So, thank you for your question. What we know about the universe is that it behaves exactly as we think it should behave. If we look at the observations, we can explain them to precision that is of a few percent or less. So we know exactly that is expanding, at which velocity it is expanding, when it was born, when was the Big Bang. We can nail down to very high precision. So everything seems to follow the equations that we know from general relativity, from Einstein, but the problem is we don't know what is making it work like this. What are the ingredients that make it work like this? It is as if you are looking at a clock. Imagine looking at a clock on the wall, and we can predict everything about the motion of the handles of the clock. We can tell you exactly how long the little end will be in 5 minutes or in 2 days and so on. So we have that level of understanding and prediction, but we don't know what's inside. What are the mechanisms that actually make it work like that? And these mechanisms are called dark matter, dark energy. So 70% of the energy in the universe is in a form that we don't even understand. So, yeah, we are in this very special situation where we think with our equation we can explain many things, but we don't know exactly the content of the universe, and so what is driving this very complex machine.
Ωραία. Έχουμε μερικά λεπτά ακόμη για κάποια ερώτηση.
So we have a couple of more minutes for one maybe last question. Thank you very much. So I'd like to ask you, can you hear me? Yes. Human beings have limited senses in terms of hearing, sight, and I'd like to ask you, when a human being started discovering the world, and as you said, we do have something in our mind, but we learn things and we confirm things much later. So how can we be sure about the things that we know, and how we could explain all the things to someone who has a very different view, or maybe somebody who doesn't understand things as well as we do?
Explaining things, scientists have learned that to explain things you have to use a common language. In mathematics and physics, these are equations. And in fact, mathematicians write their papers with just equations, because it's sufficient to read them to them to understand what they mean. It's a bit like reading music. In physics, we need also words because equations are not enough. But the point is that you need to have a common language. When explaining science to the public, we don't have the same language. And this is where my concept of cognitive empathy comes in. One has to find the right language. And of course, this cannot be a scientific language, cannot be equations. In the book, I try to do this. I try to use a language that is used by everybody, by young people who are not scientists, by older people who are not scientists. At the same time, I also teach that people should not be scared of equations. If you read a book, there are equations. So that you are, and I introduce equations, and my publisher hated this idea. They said, it's a bad idea, don't show equations. But equations, if you look at equations, you start to realize that actually they are not so difficult, and I can understand them if only someone explains to them in very simple terms. So the Einstein equations that takes me 6 months to explain to a student in physics can still be understood by you who are not knowledge of physics, by just understanding, this means that this side is about geometry, and this time is about matter. And so the equations just say that geometry is equal to matter. Again, it's learning to use a language that can be understood.
Πάρα πολύ ωραία. Νομίζω κάπου...
Very well. At this point, we will close this presentation. Thank you all for being here, and I'd like to thank Mr. Rizzola once again for his participation.